Welcome to this explainer. Today, we're going to demystify the exact recipe you need to build a Galois extension and really unlock the symmetries of a Galois group. We'll be looking closely at the foundational rules of Galois field theory, taking those incredibly strict mathematical definitions and translating them into a super clear logical roadmap.
Okay, let's take a quick look at our roadmap. First, we'll define a Galois extension. Then we'll hit the first pillar, separability, followed by the second pillar, normality. After that, we'll see exactly why we need both. And finally, wrap it up with the cyclotomic example.
All right, starting right off with section 1, defining a Galois extension, our ultimate goal. So why is a Galois extension such a highly sought-after mathematical structure? Well, in field theory, you know we're constantly hunting for symmetries, right? We want ways to map a field onto itself while totally preserving its core algebraic structure, because these symmetries give us incredible insights into polynomial equations. But here's the catch. If you have a field extension, let's call it L over a base field K, it can't just be any ordinary extension to earn that Galois title and grant us access to those symmetries. It absolutely requires two foundational pillars to work. It has to be both separable and normal. You literally need both of these conditions met simultaneously to guarantee the extension has enough valid field automorphisms to form a Galois group. Let's break down exactly what these two ingredients mean in practice.
Moving on to section 2, the first pillar, separability, our first ingredient.
Okay, so an algebraic element over a base field K is considered separable if its minimal polynomial yields completely distinct, non-repeated roots. In algebra, this translates to checking the formal derivative. Think about it. If a polynomial has a repeated root, that exact same root is going to evaluate to 0 in the polynomial's derivative too. So, if the minimal polynomial and its derivative are relatively prime, meaning they share literally no common factors, you are mathematically guaranteed to have perfectly distinct roots. This complete lack of multiplicity is the absolute bedrock of separability. Let's look at a concrete example to really see this separability in action. Consider the field extension of the rational numbers joined with the square root of 2 over the base field of the rational numbers. The minimal polynomial for the square root of 2 here is x squared minus 2. To check for separability, we just evaluate the roots of that minimal polynomial. We get the positive square root of 2 and the negative square root of 2. Since these two roots are totally distinct from one another and absolutely no root is repeated, the rule is satisfied. And if we were to take the formal derivative of this polynomial, which is 2x, it obviously shares no roots with x squared minus 2. Boom. The polynomial is separable and our first pillar is firmly in place. Now, I have to mention an incredible mathematical cheat code here. If you're working with a field of characteristic 0, like the rational numbers, the real numbers, or the complex numbers, separability is automatically guaranteed. It's true. Every finite algebraic extension of a field of characteristic 0 is completely separable. Because of this beautifully elegant theorem, in most day-to-day number theory applications, you actually just get this first pillar for free. Which brings us to section 3, the second pillar, normality, our second ingredient. With separability secured, we turn to the second, slightly more demanding pillar, normality. For an extension to be normal, it really has to act like an all-inclusive package deal. If every irreducible polynomial over your base field K that has just one single root in your extension field L actually splits completely into linear factors inside L, then you have normality. You can't just selectively include roots. If one root gets an invite into the field, the entire set of sibling roots has to be there too. As our source material puts it, if one root of an irreducible polynomial lies in L, then all of its conjugates also lie in L. This highlights the strict all-or-nothing requirement of normality that we have to satisfy. A normal extension demands that if you capture a single root, every single one of its conjugate roots must also be securely locked within that exact same field. Let's actually contrast a successful normal extension with a failed one to see how roots can kind of escape the field if we aren't careful. On the left side here, we return to our trusty extension of q adjoining the square root of 2. The minimal polynomial x squared minus 2 has the roots positive square root of 2 and negative square root of 2. Both of these are securely inside our field L. That is a perfect normal extension. But look over at the right side. We take the extension of q adjoining the real cube root of 2. The minimal polynomial here is x cubed minus 2. Now, over the complex numbers, this polynomial actually has 3 distinct roots, the real cube root of 2 and 2 complex roots involving omega, where omega is a primitive complex cube root of unity. Because our field L only adjoins that real root, it sits entirely on the real number line. Those other 2 complex roots, totally locked out. They just do not belong to L. Because those conjugate sibling roots are missing from the package, the extension fails the test. It is not normal.
All right, let's jump to section 4, why we need both, synthesizing the rules.
So, the big question, why do we absolutely need both of these specific pillars to successfully form a Galois group? What mechanically happens when we bring them together? Well, when both the separability and normality conditions are rigorously met, meaning the extension is fully Galois, something really beautiful happens. Every K embedding of L into an algebraic closure actually maps L perfectly onto itself. These embeddings are precisely the field automorphisms of L that fix the base field K while permuting the roots. And when you gather all these valid automorphisms together, they form the highly coveted Galois group. Mathematically, they behave exactly like physical symmetries, rotating a complex geometric shape perfectly into place, leaving the overall structures seemingly unchanged, even as all the internal components shift around. Separability ensures we have enough distinct roots to map to, and normality ensures all those mapping destinations actually live inside our field. But without normality, this symmetry literally shatters. Elements escape the field. When you try to map the field using those K embeddings, some embeddings will send elements of L completely outside of L, just like those complex roots of the cube root of 2 that we just saw. Because those elements land outside the field, the mappings are no longer valid automorphisms of L. You immediately lose the symmetries required to form the full Galois group. The whole thing just falls apart. Let's move into our final section, section 5, the cyclotomic example, putting it to the test. Let's put our entire 2-ingredient recipe to the test with a classic real-world application. Let L be the rational numbers adjoined with zeta, a primitive root of unity, and let M be the rational numbers adjoined with zeta to the power of Q. We want to know, is this extension L over M Galois? Well, let's rigorously check our pillars. Requirement 1, is it separable? Yes. As we already learned, we're dealing with extensions of the rational numbers, meaning we're in a field of characteristic 0, so separability is completely automatic. Requirement 2, is it normal? Let's check the minimal polynomial of zeta over M, which is x to the power of q minus zeta to the power of q. The roots of this polynomial are precisely the elements zeta multiplied by the various qth roots of unity. Since all of those resulting elements can be generated within L, the polynomial splits completely into linear factors right inside L. No conjugate roots escape the field. So yes, it is absolutely normal. By successfully verifying our 2 foundational ingredients, we effortlessly prove that this cyclotomic extension is indeed Galois. Plus, because its Galois group has an order of Q and is generated by a single automorphism mapping zeta to zeta times a primitive qth root of unity, we can definitively call it a cyclic Galois extension. We've seen how remarkably strict definitions lead to such beautiful, elegant symmetry. And this leaves us with a fascinating final thought. If identifying something as complex and powerful as a Galois group just comes down to rigorously checking for separability and normality, what other deep mathematical symmetries in the universe are waiting to be decoded with a similarly elegant recipe? Thanks for joining me on this explainer, and keep exploring those symmetries.